Hi everyone, today we're talking about Boltzmann generators and what losses to use to train them.
So hi everyone, so thanks for the invitation. So I'm Guillaume Charpia from the TAO team, which is an INRIA team located at University Paris-Saclay in Lyssen. So the team focuses on deep learning mostly these days, like it used to be machine learning and optimization, so mostly neural networks now. And I've been working with Jérôme on that particular topic that is going to introduce, and we supervise together a PhD student, Loris Felardos, and the most of the work we're going to present is from his PhD.
And so I'm Jérôme. I'm a researcher at CNRS in Paris, and I'm not a computer scientist. I'm more of a physical or chemical biophysicist, let's say. And the lab here, in the lab, we do molecular simulations of biological systems. But sometimes we get frustrated with simulations, and so we want to try something else. So this is kind of how I got involved into this. And with that, maybe I will, let me see, maybe share the screen and start presenting.
Very nice, very nice.
There we are.
And yep,
Can you see it?
I can see.
Okay, got it. So yeah, what we worked on was going towards data-free generation of molecular configurations with normalizing flows. So the first author here is Loris, who has moved on. So we're going to be presenting the stuff. So the problem, the task we have is to sample a Boltzmann distribution. I'm going to, present the general stuff. I assume not everyone, the audience is kind of diverse, right? So maybe a bit of back. No,
I think
people are.
you
Go
can
quickly.
assume quite a bit of familiarity with Boltzmann. What is the Boltzmann distribution?
Excellent.
What do you want to do here? What is alanine dipeptide? We've had this sort of stuff here a bunch of
Okay, fair enough. So everybody here knows this. So I'm just going to introduce our notations then. So we call it PB, and we call the corresponding physics-based energy UB. And sampling from this lets us, get valid, make predictions in physics, chemistry, biology, material science, anything that can be described by a physical energy function and sampled at a certain thermodynamic temperature. So far, so good. So this is what we do in my field, in my lab, using molecular dynamic simulations. So for that, approximating the energy function, UB, and approximating the physical dynamics using, for example, a Langevin equation, where we have a potential energy gradient, friction term, temperature-related term. And what we find with this is that we generate trajectories that are metastable. So we get many different modes in the distribution, and the modes are metastable. We get long residence times. Our simulations are short compared with the relevant timescales for relaxing between these modes. So in practice, the statistics are really hard to converge. So this is a very expensive story. Hence the idea of going to generation and say, let's take a known prior distribution, if you will. Let's make it something we can sample easily. Let's learn a mapping that will project it onto a relevant distribution. And in principle, any kind of generative model might work. That is, generate something that looks like what we want. The problem is we don't want something that looks right, as in something that will trick a discriminator network. I mean, what we want is we want to generate correct statistics because we want to make quantitative predictions. And so models like, typically, or until recently, should I say, GANs or diffusion models did not offer statistical guarantees. So you get biased samples and you have no need to know where to work with them. So what we want here is we want to be able to estimate the generated density precisely to debias, either by reweighting the samples or by resampling them, metropolizing them, if you will. And so the scheme becomes, you learn it by ejection, you go both ways, you can train the energy of generation, UG, like PG, to approximate UB, and it doesn't matter if it's not perfect, and then you can debias, and then compute stuff and profits. And so that has, famously, the famous example that has come to light and been applied immediately to biological molecules, like here, is the Boltzmann generators, of course, and maybe started the whole show, although we were kind of working on this already at the time, so it was big news to us when this came out.
Wait.
And yes?
So because you're actually on the molecule physics side of this, and you run your MD simulations, and you actually use this stuff that I also try to build, right, and hope that it's useful in some way. But then can you maybe speak to how useful are things like Boltzmann generators? Do you actually use something like this
For science?
Yeah.
No, and I don't know anyone who does.
And do you think there are some people that use normalizing flows, for example, to do map between the distribution of high temperature to low temperature, and accelerate some simulations there? Or
yes, I think there's some interesting work being done there. I think another aspect of this work that was really interesting to me in this paper, so first, when we read that, we thought, okay, maybe we need to all retire now because simulations are over. And then we looked more closely and we said, maybe not. But one aspect was the free energy estimation work that is done here, meaning once you have this mapping between, say, a mode that you can easily sample and different modes of the target distribution, that's the other way around, but anyway, that means that you can compute free energy differences between the input space and the output space, and you can compute free energy differences between states in the output space or between two different states. So there are a few examples in that 2019 paper of Frank Noe of estimating free energies between those, and even the free energy estimation task, given decent sampling, is pretty difficult. And so that's a way to regularize the problem of free energy estimation. But in that respect, that's kind of a generalization of something that was done by physicists before, which is called Frenkel-Ladd, which was basically when you have a solid, you compute its free energy, its absolute free energy, by reference to a simpler system, like an Einstein solid, where each particle is just a harmonic oscillator and they're uncoupled. So you know the exact free energy of the system. And so what you do is you reduce your system to a simpler system that you can compute exactly. And then if you can, I've never done it. But anyway, so there was something in the air about this. And this is kind of a new instance of this approach, but using a network as the mapping. I mean, from known to interesting system. Yeah?
But here you have a very so your Einstein solid here is just a Gaussian distribution set, and it's its partition function. But yeah, I wouldn't if you have this Einstein solid, is it as simple as a Gaussian distribution as?
Precisely, because each particle, you have a network or a lattice of particles, and each of them is in harmonic well. So it is literally a multi-dimensional Gaussian.
And would the physicists then do something like AIS between the Einstein solid and their crystal and get the free energy difference and then do
something like that. So I'm only aware of the existence of the theory. I haven't looked in detail at the numerical implementations, and I know it hasn't been. I think it's only usable if you have significant, of course, considerable overlap between the Einstein solid and the real solid. So you're going to use that for simple materials. As soon as you have, don't think of that for biology, right? There have been an intermediate stage was to take a protein, and that was done in the group of Martin Karplus, who got the Nobel Prize a couple of years ago. And that was called a confinement approach, where you take a protein and you want to turn it into an Einstein solid. And what you do is you just add confinement potentials on every atom, So you trap each atom in a harmonic well. And once the harmonic well becomes steep enough, you make it increasingly steep. And once it's steep enough, the harmonic well dominates all the rest of the interactions. And so the atom becomes just a little Gaussian. And if you can compute the free energy of the process of adding these restraining to this harmonic well, then you have a connection between your real ensemble and the Einstein solid.
Okay, and now we're already talking about free energy difference calculation and
yes,
and so, but then why do you want to train data free? Like if we, for example, have our little bit simulation for this crystal,
yes,
little bit simulation for the other crystal, then let's just train our Boltzmann generator from the Einstein solid to the crystal, and on the other side with data and also data free. Like,
so that's the trick. We don't really want to train data free,
okay.
But if we want to train with data, with a limited amount of data in a really robust way, the objective of data free means robust to incomplete data, to partial, to biased data, to everything. So it's really an objective of robustness. Data free is kind of an endpoint that we don't actually want to reach, because you're right. I mean, a little bit of simulation is cheap, but we know simulation is going to be biased and something and have a lot of problems. So that was really going for robustness.
Okay, so
lack of data.
So what do we do here? Let's improve the data-free training. So when we combine it with our data training, we get the best stuff.
Exactly. Once you add the data,
how to do that?
Yeah. So you'll see. So okay. So the limitation at the time was that you really need data from all modes if you wanted to get all modes in the output, and so that there was a high requirement of in terms of discovery of the modes. All the exploration had to be done beforehand. And this the system I'm showing here on the left was really what talked to my community, because we simulate proteins. This is our job. And when you see that, you say, wait, this is like they're stealing our jobs. And what they did here was, I want to say, a little bit egregious, because what they really do is they start from simulations, yes, from all modes of the distribution, yes, and then they do a PCA on that data. So they already learned the structure independently from this Boltzmann generator. They learn the structure of the space, and then they reduce all multimodal degrees of freedom to a very small, very low dimension space. So the network has almost nothing left to learn. The network is mostly Gaussian in, Gaussian out, right? And everything is condensed into a few degrees of freedom. So they've simplified the task for the network immensely here based on the information they had beforehand. So this is absolutely not transferable to a system where you don't have as much knowledge. And this is the reason why this came out 4 years ago, and no one has really used it to sample proteins since, that I know of. Of course, the technology has gone a long way since, right?
Yeah, if I want to compute, I mean, I fit my normalizing flow, it works nicely, and now I can compute free energy difference between open and closed state, and then
that is nice. Absolutely, that is very nice. But then it's not a it's very different from sampling from scratch. It's like once you know how to sample it, then you can you can do cool stuff. Absolutely. Absolutely. Okay, so training. So yeah, we want to train in the absence of data that was exaggerated, but in the absence of extensive data. So energy-based training, fine. Wait, am I? Yes. So for that, you need to compute the energy. So we use the classic energy functions that are used for biomolecules. There is some need for regularizing. That's what we found, because these functions are very ill-behaved. They have pretty bad singularities. So what we found was that a gradient clipping approach was pretty effective. So typically, this is this 1 over R12 term divergence, and then having a constant gradient below a point preserves the structure and removes the singularity in the gradient. And then, of course, we need to compute the energy of generation. And so here, this introduces more notations. So to make sure, so our Gaussian prior, the points are called Z, and Qn is a normal distribution. General distribution, yes, PG, and our target is PB, Boltzmann probability, and QF is the backward image of the Boltzmann distribution in the latent space. So we need to compute the inverse. So I'm going to skip these very basic reminders about computing the density for the image distribution. So for flow-based models, you need this kind of coupling blocks. This is all explained in now pretty old literature. So basically, these are the same architecture that are used in Boltzmann generators. So maybe getting more precise, right? Training. So to train, you need losses, and right now we have two spaces: latent space, and in the latent space you want so in the target space you want the generated probability to approach PG to approach PB, and in the latent space you want QF, which is what you do if you take Boltzmann and map it to the latent space to approach a normal distribution. So you can compute a KL divergence in this space on the left and another one in that space. And the one in this space, if you write it as it comes, uses an expectation value with respect to PB. So you need data distributed according to PB. And if you look at the one on the other side, if you write it naturally, it's just a normal expectancy with respect to normal inputs that you pass through the network. So this is naturally data free. So the problem is, so the training tasks we use are intentionally very simple. And I think the philosophy here is, if you want to sell a method, you ask, what is the hardest task it will succeed at? And if you want to really improve a method, you say, like, what is the simplest task that it will fail? So we tried to break it. And so we used, at some point we started with small molecular system and we wanted to ramp up, and we ended up trying to try and make it more robust by going to even simpler systems. So we started with a double well system, but this double well, we increased it in dimensions. So it's bimodal in one dimension, and there is 11 more dimensions that are unimodal. So basically we have a 12-dimensional system, but it's only bimodal in one dimension. So it is extremely simple, and it can break a lot of stuff already. So there was a way to pinpoint the problems we had. And then we have our classic friend dialanine, and then we wanted it even simpler. So butane was used for some stuff. And then, okay, so there's the whole thing of handling properly molecules with equivariant networks and everything, and we decided to set that problem aside because we focused on the loss question. So we had a simple way to deal with hydrogen atoms to remove some of the symmetry issues. So basically, what we did was to first do a pre-training using simulation data, and then see if we could fine-tune the generator and if it was stable under fine-tuning in the absence of data. Because so really stability was our under energy-based training was our criterion. That's what we wanted to achieve. Because we saw that if something is not stable under energy-based training, then even if you add data, this instability will show up somewhere, right? And there would be a tendency to instability.
So what is what coordinates do you use to represent
So the coordinates are Cartesian coordinates. So that is intentionally we decided to not make the task any easier for the network because they're already tiny molecules. So, there is no. So what we did was Cartesian coordinates, and then with some alignment, basically align Cartesian coordinates.
Okay.
Yes.
So you use Cartesian coordinates with some coupling flow, and you RMSD align them to some reference frame.
That's correct.
Okay.
That is correct.
Good. Yeah, I like that a lot, right? Because now the alanine dipeptide plots or the round Chan plots that we look at, like we're not just outputting an angle that basically is then already defined.
No, exactly. We're outputting Cartesian coordinates and then trying to match that. Yeah. Yeah, definitely. Which is, in a sense, you could say it's not the best way to go about it, right? You want to use a graph and a better representation, but you can always do that later once we make the loss more robust. And anyway,
maybe not the best way to go about building a Boltzmann generator for a molecule, but a good way to go about testing different ways to train a Boltzmann generator.
And we ended up going back to the double well system anyway. So then the representation problem got away. We could, we can make things succeed or break just by tweaking the double well. So it was even easier to understand what was going on. I mean, that was the goal.
Okay.
So of course it's a bit less sexy, right? If you can say we can successfully generate a double well, it doesn't make it to science, but it was a way to move forward on the loss issue. So basically, I'm going to skip some stuff. What happens is, so typical stuff, and there's a color code here. So let's look at the color code. So the orange stuff is data from simulations. And then pink is pre-training using, based on the simulation data. And blue is fine-tuning in a purely energy-based fine-tuning. So what happens? So this is a simple double well. So easy. But then as soon as you either start with a poorly pre-trained system, then it gets unstable under data-dependent, under data-free fine-tuning or energy-based, then it collapses to one mode. Or if you add flat dimensions, so if you have this 12D systems with a lot of, if the other dimensions are kind of elongated Gaussians, then you get collapse again, which is kind of crazy if you think that how simple the topology of this thing is. I mean, there's really kind of nothing to do, and still. So there is a very interesting instability there that got kind of irritating to us, and we wanted to get to the bottom of it. And then, so one solution that was advocated already in the 2019 Boltzmann generator paper was to make a little linear combination of both losses, a little bit of data dependent, and then the so-called ML loss in that paper, and then a little bit of energy-based training. And really what they did was more like 98% data dependent and 2% energy-based. So energy-based was more like a little refinement, add-on into the loss. And when we do that, what we find is you don't solve the collapse problem. You get kind of a mix, something that wants to collapse, but the data tries to keep it in. But that's why I was making, having data is not a substitute for having a stable loss.
So Vincent is asking in the chat, does the model incorporate any of the system symmetries, rotation and translation invariance? I assume not, right?
No, well, in this case, the system has, I guess so. Yeah, this is the double well, right? So this is a absolutely toy system. You could say it has this symmetry with respect to there's not really a representation issue here. We kind of evacuated those questions to focus on this because, again, we can break something very simple. So we don't need to worry about the complicated molecular features and the question of symmetries. Yeah. Okay. So one thing we did find is that we can mitigate the collapse problem by increasing the temperature, the generation temperature. That is true. So that's a.
I mean, but then you don't get the distribution you want to sample.
Oh, you can reweight.
Yeah. Okay.
I mean, that's it's an important sampling.
I can also reweight from my Gaussian to
yes, yes, exactly. I mean, but you know, it's what I mean is that this is a typical yeah, you could say this is like modifying the energy. It's like smoothing the energy.
We're going to speak about it in the next section.
Okay.
Actually.
Yeah. So okay. Yes. So reweighting. Yes. Yeah. I mean, you see, this is reweighting with the overlap, depending on the kind of temperature changes you do. Of course, this doesn't carry over well if you go to high dimension, right, and biological molecules or something. That's true. It's kind of a remark in passing, but we don't really advocate that as a solution to the problem, for sure. So what you can do is you can take this other, this loss in the latent space, in Z space, and instead of inputting data from simulation, so data that is expected to be Boltzmann distributed, you can input points that have already gone through the generator. So you generate, Gaussian samples, input them to the generator. There you detach them, reweight them to get an approximation to the, or to get, anyway, a discretization of Boltzmann, and then compute the loss, go back through F and compute the loss there. So that means that, yes?
Then, right, this is the sort of thing where we train with forward KL, but the data that we use, we generated ourselves, right?
Yes.
We generate some data, we detach it from the computation graph,
yes,
and we reweight it as well.
Yes.
And now, dear Vincent Stimper, flow annealed importance sampling bootstrap, right? I generate my XG, and now I would then reweight it with with annealed importance sampling. Is that right? And then use that sample as
so WI is the reweighting factor. Yes.
Yeah, but I think in flow annealed importance sampling bootstrap, the difference would be that also the X actually changes, and we don't only reweight it.
Yes.
Because we do
the
absolutely importance sampling.
Yes. So yeah, this is a simpler, this is like the basic version, but it's actually used just at the point of comparison. Maybe we shouldn't dwell on that too much because we're not going to end there. So basically this is nice, but it's very peaky. So you end up, depending on where you start, you end up just discarding most of your data, right? And putting all the weights on a few samples. So it's not really usable. So basically we just ended up seeing that you find different behavior. So wait, that was an old, so that was one version where we didn't properly align stuff. So of course it didn't work well. So I'm going to skip stuff about alignment. And the bottom line is, so again, dialanine simulation data, pre-training using simulation data, we're fine. There's a little stream, connecting the small mode here to the rest. And then fine-tuning, we get collapse, we lose this. And so I don't know where this appears in random orders, but basically, so this is projected onto this angle here. And you can see, and this is so the Boltzmann energy of simulated samples, orange, and generated samples. And what you can see here on the other side is generation energy of simulated samples. And here in this minor mode, I'm sorry, it's projected onto the other angle, onto psi. And of course, these samples here have a very high, most of them, that's interesting, they're kind of continuum. So most of the points here have a very high generation energy, and there's a little stream of, there are very few samples of this set that have a low-ish generation energy, but not enough. So we have this instability, and as you fine-tune,
well, wait a second. So what are the energy plots that we're looking at here?
So the energy plots here are,
we take simulation data, right? And then look at the energy under our Boltzmann generator.
Exactly. This is the generation energy for those, right? So basically you have to, make them backward. Yes, exactly. So you can see that basically these points are points that have no chance of being ever generated by the fine-tuned generator. But interestingly, so what we wanted to see is that, because, sorry, when you sample, why does it not appear? Here. When you sample here, you don't see anything here. So you don't really know because this is so unlikely. But if you take now these points, these simulation points that are here and look at their generation energy, you can actually estimate the generated density in this region quantitatively. And that tells us that some of these on the sides, the generated density is not, like there are some areas where generated density is not so low, but most of these points, so most of this space has a very high generation energy.
Yeah.
So this is a way to dissect what's happening to the generator and why this mode is disappearing.
Right, like generation energy, we can just maybe in our machine learning speak more understandably say the likelihood of these points under
Absolutely, yes, like very low likelihood, if you will, sure. But still, what's interesting is that the correlation between the target density and the likelihood is pretty good, because this is kind of a minority of the points. So from a distance, like this is, anyway, we find this analysis to be helpful, this visualization. Okay, and now it's high time I let Guillaume present the rest. So I'm going to stop sharing.
Excellent, thank you. And Guillaume, we are excited to hear more.
Okay, so can you see my screen?
Yep.
So we spoke so far about the collapse problem, and now we're going to study slightly more and propose other losses for the same task. So first, so here we had really an issue with the KL loss that on the paper it looks nice, but when you try to optimize it, it's a nightmare. So why so? The first reason is that the Kullback-Leibler divergence is not a metric between distributions, it's a divergence between probability distributions. And the fact that you have this constraint that the probability distributions have to sum up to 1 in terms of mass, this is really important. And in practice, when you're going to optimize the KL distribution between the KL divergence between two distributions, you're not going to have the full distribution and make an integral. You're going to have a discretization over mini batches. And however large can be these mini batches, they are going to be very small compared to what you need to really estimate the full distribution. So that's the issue with high dimensions. And if you don't do anything there, you just naively discretize into mini batches and compute KL divergence, and forgetting that you have to put probabilities there, then what you get is something very fun that you can really prove, like just in a few lines, that if you take always the same mini batch, then the Kullback-Leibler divergence between what you generate and the target on that mini batch is not going to converge to the right quantity. It's going to behave like this. I mean, it's it makes no sense basically. So now, if you you care a bit more about this and you do the proper normalization, then you have to think about the meaning of the normalization. So basically, you're comparing a distribution which is a set of direct peaks on some very particular points, and you're comparing the densities there. So what's the meaning of that? That's another question. So to bypass this kind of issue, what we want is to consider a loss, typically the L2 loss between densities. This is something very simple, and mathematically it's not something that is recommended to just take the L2 norm between densities. But the good point of this kind of criterion here is that if you take any mini batch, for every sample of this mini batch, basically you're going to push the probability of generating that sample towards the true probability with which it should have been generated. So at least for the point you are sampling, you're doing the things correctly. So actually, you don't have to exactly take the L2 norm. It could be like the expectation of the square of the difference here under any reasonable law. So the law could be PG, the law could be PB, whatever. Provided that there's no point that is important for which your law is as density 0, this should work after a while. Difference, if you take one law or another one, is just going to push at different speeds the convergence at different locations of the space, but in the end, it will converge to the right point, to the right distribution. So if we just do it like that, and we try, so we need here to the formula for the what we generate and to compare here. So we'll see that we will need the partition function of the Boltzmann distribution. So to bypass this, there's another trick that you can look at pairs of points. If you look at pairs of points and you try to compare things, then by looking at the ratios between the quantities at different points, this ZB factor is going just to cancel out. So in the end, you just have something like this. So here I'm looking at the ratios between PB and PG at a point, the ratio at another point. I put log because usually with logs, we see things better, right? When we speak about probabilities. And so we have just the square of this difference here. And that's it. So basically, it's natural to obtain this kind of formula. And so one point is that we don't need ZB anymore because we're comparing this the ZB at one point to the one at another point. So it's the same quantity. It's symmetrical. It leads to the correct optimum if you try to optimize it. And actually, it's convex in UG. So it's not convex in the parameters of your neural network, but at least it's convex in the quantity you try to optimize, which is the output. Actually, not the output, but the quantity you compute from your network. So at least it should push UG in the right direction. So UG is just a minus log of the probability of generating that point. So if we do it, and it gets better, like we have the original distribution, we have a system that each strain according to it, like using the samples from the distribution, and the fine-tuning gets better than before. At least we don't lose the mode. It's disappearing a bit, but it stays there. So this is results after convergence. Okay, this is not going to disappear here. So it's getting better. But for this to work, we need other tricks. So I said that we could take any law to sample the points where we're going to compare densities. One possibility would be to compare to sample the points according to PB. In practice, we see that we have some issues. If we try with PG, we have another issue, which is that if at some point there are some modes that are very minor or that are already lost, then the modes are going to stay like that. We're not going to recover most that are lost. And so what we do actually is a mix of both. Like we sample one of the points with PG and the other one with PB. And then actually it starts to work, even on the dialanine that we found like more difficult to generate. So another trick here that is very important is that we need also masks on the quantities we optimize. So this might look very strange, but when we compute the gradient of such quantities, so we have, of course, the gradient of PG according to its parameters. And if at some point we ask PG to decrease because this PG is too high compared to the PB, the target PB here, so what's going to happen actually in practice is that imagine that this is a PG distribution and we have a bit too much. I suppose you see my mouse. And you ask the PG quantity at that particular point to decrease. What's going to happen is that the normalizing flow is going to change the directions in order to spread this mass all around. And what does all around means is that you have like typically 40 or hundreds of dimensions around. Most of them are very bad. So actually it's going to push the mass in direction it should not. And this is really a problem. So what we do is that when the gradient pushes PG to decrease, then we don't apply it. We apply it only if PG is asked to increase. Okay, so it sounds a bit strange. So we are going to see a next slide. Oh, actually, a bit later. So another trick before I speak of this is that another thing that improved the stability of the training was actually to use a cache, like the same as in reinforcement learning. You have some samples, you train, and you keep some of the samples to re-inject them later. So here, the idea is that if you have particular points that are particularly undersampled, like for example, a mode that is disappearing. You keep some points within that mode, and you re-put them in later mini batches to be sure not to miss them. So that is quite simple to do. So it improves the stability, but it's optional in the sense that if you don't use it, you can still make it work. Wait, that was a question?
Oh, sorry.
No. So let me continue then about this loss again. So that is linked to the question that was before about importance sampling. So in the end, what do we want actually? What do we need to train such networks? In the end, we want to estimate statistical properties that look typically like the expectation over the true distribution of something. Okay, usually it's like this. It's kind of quantities that we really want to compute. This actually is writable this way, okay, with a target distribution and the one with which we generate. And here we see this factor of importance sampling. So we might say, actually, I could take any generator, provided I have this importance sampling factor here. Actually, when I compute the integral, I'm getting exactly the same quantity. So whether I have a generator or another one, in the end, it will be exactly the same. So what's the point here of optimizing anything? The point is that in practice, we're not going to compute an integral. We're going to discretize over mini batches, and we're going to compute expectations these ways, like with Monte Carlo schemes. And what's the difference between this estimator here, like derived from one generator or from another one? The difference will not be the mean, because on average is going to be the same. It's going to be the variance. And actually, if we dig into that and we develop this expression here, like what is the variance of my estimator Q here, given a certain generator G, then actually you obtain something like this, which is just the expectation of the ratio PB over PG squared. So basically the variance of this quantity that you can rewrite in a bunch of other manners actually. It's also the expectation over PB of PB over PGs, and that looks a bit like Kullback-Leibler, except that the log is missing. And this is actually the exponential of some Renyi divergence, the one of order 2, between PB and PG. And also this is a variance over PG of just this ratio here. So we see that there's quite many different ways to write this quantity that indicate that it might be a good one, like it's a divergence at least, and something very easy to compute. Okay, so if we wanted a criterion to train a generator, actually, since what matters is the variance of this estimator, this is a quantity here that we would like to optimize. Okay, so we're going to focus now on something like this, except that we're going to add a log. That's first modification, we add a log in front of the ratio to make things more stable. Like when we speak about probabilities, usually we speak about log of probabilities. And we're going to incorporate all the previous remarks about the fact that if we try to decrease PG, it doesn't work. So we're going to have a bunch of tricks here. That is, if the log ratio is lower than the mean over the mini batch, so at that particular sample, then we discount that term. So basically, we're cutting the gradients where they're pushing in the wrong direction somehow. And also, we are not differentiating with respect to a certain number of things. So the mean here is not differentiated either, for the same reason, actually. If we try to differentiate the mean, probably it's going to push it in the wrong direction. And as a consequence, all the samples that contributed to the mean, K is the mean of the log ratios here, the mean of the R's, is going to push things in the wrong direction also. So in the end, we end up with a formula like this that might be debatable. Like we have lots of very curious choices. Well, not curious, but at least it's not a gradient descent anymore. Okay, like we are cutting parts of the gradient. So it's not a gradient descent that we're performing anymore. But the good news is actually we can show, like we can prove theoretically that minimizing this quantity is still going to converge and to the right minimum. So we are changing the way we optimize the quantity, but in the end, we are actually optimizing the true one. Okay, so that's was not something completely obvious. So the thing from the practice could be justified by the theory. And digging on that on that track, actually, there are two papers who appeared either in parallel or later. Vargrad, actually, is a paper by Richter and al. That shows that if you take the true variance here, and you take the derivative of it, so the derivative of the variance of the log ratio, actually it's exactly the same as the gradient of the Kullback-Leibler divergence. Okay, so that's a very funny link that the quantity that naturally would like to improve, like the quality of our estimator for the final thing we want to do, is actually the same as the Kullback-Leibler divergence. It's the same gradient in both cases, up to the fact that in the end, when we discretize these quantities, and so we get different estimators, and the variance of these two estimators is not going to be the same. There's another paper here also that uses a different way to compute the gradients, and they prove also, well actually the intuition is that having a different estimator of the same quantity is going to decrease the variance of that estimator. So I'm speaking about the estimator of the gradient. The issues of which are due to the fact that we can't sample all points ever in the distribution, but we only have mini batches, and even for large mini batches, we have problems. Okay, so results. So with all of this, in the end, it kind of works in the sense that if you start from a pre-trained model with data, and then you continue training it without any data, we don't lose the mode. So actually, this is better than what happened with KL divergence before, the pure KL approach. Okay, so basically that's what we already showed before. And so here we see the ratio of the minor mode here, so the quantity here, the proportion here, with respect to all the mass in the whole set here. And we see so that it decreases, but after some while, it's maintained and doesn't go to zero. And that's the behavior we wanted to get. So in that sense, we succeeded in shaping a loss, in designing a loss that is not going to get rid of the minor modes. So we are still not able to learn from scratch with this loss. That is, if you get just random distribution at the beginning and we try to minimize that loss, data-free, so without any example, it's not going to work. But at least if we fine-tune, we don't lose the modes. So in that sense, we've made progress on that.
Guillaume,
yes.
There's a question from Vincent there, which is a very good one, which is why is the small mode less populated? And that's just a reason due to the kind of bad representation we have for the molecule. So right now we generate heavy atoms only, and we add hydrogen atoms to the separate layer that's deterministic. So basically, it's kind of a crappy way to generate molecules. But so if you take the idea is if we survive this now, if you replace it with an architecture that properly generates molecules, then we won't see this discrepancy. That's only due to the kind of poor representation, which was kind of not what we optimized here.
So can you specify like what the architecture is? So you're basically fixing the bond distances of the of like, I don't know, the hydrogen atoms, like the distance of
not even that. We have the generator generate only heavy atoms, and then there's a secondary network that produces hydrogen atom positions conditionally on the heavy atom positions, but it's not a proper conditional distribution. It's just like deterministic placement. So basically it kind of produces minimum energy hydrogen atoms. It's something that is, we know it's not good, but again, that's not what we focused on. So
okay, so given the heavy atoms, you then just place the hydrogens wherever basically they minimize the energy.
Pretty much, yes. And the network is trained to do that.
Okay, so but I don't really see the connection to why this weakens the mode. And I mean it also
so the reason is
train on data, right? So like
so
if it would be model specific or architecture specific, then I would expect it to happen with both losses, right?
Yeah, so if you read the preprint, there's a little appendix on that where we derive the reason why. Basically, we train the network to generate a slightly. This network kind of shifts the target distribution when training the generator. And so numerically, you can estimate that this essentially introduces a bias in the target distribution, and this bias is what weakens the small mode. So it's kind of an yes.
But this can be corrected. It's just that we had a bad way of adding the hydrogens, and we realized it a bit late.
Yeah,
but,
and
we can correct that.
Yeah, basically, you need to use a different architecture to properly. Yeah, just generating hydrogens with a conditional normalizing flow would fix that. Really.
Okay, so as a conclusion, we succeed in having a data-free loss that does not collapse. Okay, so we are still not able to train from scratch to train from scratch networks, but at least fine-tuning is stable. So for this, we had to introduce different losses. And actually, it's when you ask people who actually try to do this kind of stuff, and when they have good results, and you ask, okay, how did you manage with chiral divergence? And they say, we didn't use chiral divergence because we never succeeded in training with it. So I think raising attention on the fact that optimizing the Kullback-Leibler divergence, I mean, it just does not work. It has to be done. Okay, so that's what we try to do in this paper here. And so within the list of things that were important to make things work in the design of the loss and the optimization, so basically decreasing PG or PB, it's the same, so I skip that part. Just for the reasons I explained, that it's spreading mass in the wrong directions, that has to be avoided. So either like we did by just cutting the gradient, or any other approach that minimizes the impact of this, or redirecting properly the extra mass to the most second promising directions. We had to be careful also about extra degrees of freedom, but were like generated really bad behavior from the network. So you have to be careful about that. And something that we saw also, that if you train at a bit higher temperature, then it's going to make things easier, of course, because then the landscape is smoother. Okay, now what about the future? So one thing we didn't do in that paper is to consider hierarchical architecture, and that should help a lot. Like having, so we had a kind of hierarchical architecture in the sense that we produced the heavy atoms and then the hydrogens only. But you can have several hierarchies or train everything properly, which we haven't done. But actually, this has been done in a recent paper here by the team of Roscoff here. We have actually learned the good way to represent hierarchically the quantities here for molecular conformation generation. And you have to see here that if you try to, as we did here, try to generate everything at once, or really in several steps, is very different. Like the number of dimensions is really not the same. Most of the dimensions come from the hydrogens atom at the end, whose location is more or less deterministic. So, or at least it could be most of the time, like just added in the end, or a good way would be to do that conditionally properly. But most of the degrees are here, and most of them are completely useless. So of course, it's easy to completely lose the point of the task within all these degrees of freedom that are not important. Second thing is, if we really want something that is able to recover modes that it has lost, then you need some kind of exploration. So either you do it with reinforcement learning or any genetic approach or whatever, but we need something that explores around to be able to recover the modes that are lost. Last thing is, of course, for this to be of use one day, you need transfer learning. The point here is actually to train possibly with data on small molecules, and then to extend that to molecules that are bigger. So of course, when you see for the first time a new molecule and you are able to, with a graph NN, so if you do everything with graph NN instead, you are able to generate a first distribution that you still need to adapt somehow, because there are, for example, some particular conformations in bigger molecules that cannot happen with the smaller ones. So you need still a bit of exploration here. But at least the hope is that most of the distribution could be already predicted from the training on the smaller molecules. So with all of this, if one day this is in place, and I think like there we can really have a like it could be really a game changer in the domain, but there's still a lot of work to do here. That's it.
That's it. Okay, that's very good. Thank you for the presentation and for all the discussion. And yeah, maybe we can go back to slide 23, or if anyone else has a question, just raise your hands and we'll get to that. But yeah, maybe here on slide 23, we can talk a little bit about the losses and also this alpha-2 divergence that Vincent uses. Is this now alpha-2 divergence here the same as
Rainy 2? It's very close. It's very similar. I was just checking. Yeah, so it's basically the difference is the factor. I think it's proportional by a factor. Basically, it's funny that the two exist independently because they're so similar.
I think like the alpha divergence is basically supposed to be a generalization of several different divergences, and you know, the alpha equals to 2 is just one particular value, right? There exists also alpha equals to 0 and alpha equals to 1, which basically is equal to like the KL divergence with like having the two distributions one way and then the other. So in this regard, yeah, they're basically the same. And so I think the main difference then of the loss that you were using is this specific formulation of then having it as this squared difference, but then also only considering like the positive elements of this difference, which I find a little bit surprising, because like, I mean, usually if you have like something like a square that you want to minimize, I mean, you would get information from either sides of the gradient. So can you maybe elaborate again a little bit more on why you decided to apply this function and not include gradients in both directions?
So one thing I'm wondering, based on recent discussions, is if this hasn't got to do with velocity. So maybe with some velocity field regularization, we wouldn't need to do this masking. I don't know. What do you think, Guillaume? It's not something we had in mind, but maybe this tends to have...
The masking here is because of this this issue that when you try to minimize PG, it pushes the mass in like all around basically, and all around mostly is bad directions. So imagine that you have the butane. Butane is 42 directions, 42 dimensions, and basically only one is good. All the rest is is very sharp valley. Okay, so if you have too much mass there and you say okay, spread the mass around, most of the mass is going to choose directions that are actually extremely not good, and it is going to make the training very unstable.
Yeah, but I mean, on the other side, you also don't want the distribution to be super peaked, right? So basically, I mean, I see the problem, but on the other side, you also want to spread the mass across some of the dimensions. So I think like how this is often mitigated with Boltzmann generators is that if you use internal coordinates, for instance, like a pure internal coordinate representation, then typically it is not that much of a problem, because like if you have internal coordinates and everything is normalized, then, you know, if you make the bond distance a little bit larger, it's not a big problem, because like since it's normalized, like in Cartesian coordinates, this will only amount to a tiny difference. While, you know, if you're represented in Cartesian coordinates, I agree that if you increase the distance too much, it can be catastrophic, because like the bond distance typically needs to be confined to a very small interval. So
of course, the representation is very important. Like the better representation you have, the better optimizations you're going to get. But I think here it's something different. Is that what you would need here for things to go properly correctly is to have like a kind of PCA of what's happening around, and say, when I spread things around, go along this axis first, like to penalize pushing the mass into the directions that don't make sense.
Yeah,
because
in a sense,
whether you have the local coordinates or the Cartesian one is going to be is the same. Like you are going to have lots of dimensions that are not good anyway.
Yeah, but I mean, in theory, this should be determined by the gradient, right? So if like, say there's one direction where you have more like a valley, and in the other direction, you know, energy increases steeply, then also the gradient in this direction where the energy increases a lot should be relatively small.
I mean, the thing is, we have a process here which is a gradient descent. It's an optimization process that has lots of issues, and how to say, I forgot what I meant. So either we design the loss correctly so that the gradients make sense, but we have to be careful about that the gradient doesn't push in all directions, but by design of the loss, it pushes in the right directions, or we have something in the optimization that say explicitly where it's not bad to push, like by favoring some directions among others, which can be justified also from the optimization point of view.
Okay. Then
so there's also the thing about the speed. Like the more clean the gradient is going to be and push in the right directions, and the faster you're going to be able to go. That is, the learning rate is going to depend heavily on that, on the quality of the gradient.
And how would you distinguish the good direction and bad direction?
Statistics, I guess. Like if you are able to get that's I mean, tracks for research, right? If I knew how to do it exactly, I would have done it, and that would be a past story already. But basically, you have your generator, and I guess that locally around the point, you can try to estimate which directions it is more likely to explore, right? Based on I don't know, gradient with respect to inputs or something like that, based on the Jacobian. So maybe there are ways to approximate this in a way that doesn't cost too much. I don't know. But this is also close to another way to do with that. You could also try to keep the full simulation, like the molecular dynamics, and say, I just want to increase the speed of these simulations instead of just replacing everything with a neural network that's going to sample IID directly. And in that case, it might be possible to make these simulations faster by directly pushing them into the right directions. Like if we do like local PCAs, again, like around the place we are at right now, we see we could get the shape of the valley basically and say, okay, we push in these directions and not in the small oscillatory direction that are say making everything unstable. I think, Jérôme, you had there are lots of approaches like that already in the classical literature, no?
Sure. Yeah. Yeah, they don't come from the idea of generation, but yes, of course.
Okay, then I would say good discussion, good questions. Let's have a last question from me. That's maybe not so good. Dialanine versus alanine dipeptide. Am I correct that dialanine is not the same as alanine dipeptide?
Actually, the thing we're looking at is neither dialanine nor alanine dipeptide. They're both like wrong names, you know, but I think biochemists have given up getting people to name this correctly.
Okay.
The real name is too complicated. It's like N-acetyl and something. I forgot now the name, but anyway. So, but I think those two names, though, they're used incorrectly. But in my experience, they used to talk about the same molecule. So I've seen them used almost so maybe some. Yeah, I've seen them used interchangeably. The problem is, since they're incorrect to begin with, it's a bit hard to be pedantic about them. You know.
Okay.
Although, so the real dialanine would be a bit larger and have, right, it's slightly different, but yes.
Well, I'll just surrender and accept that.
Yeah. So this is like the traditional version of dialanine, or what is traditionally called dialanine, for simplicity.
Dialanine is not alanine dipeptide, but everyone uses those two terms for the same.
No, I think it's the opposite. I think, wait, dialanine and alanine dipeptide are the same thing. They mean the same thing,
Right.
but they don't mean the molecule that we're looking at. Right.
Okay.
So dialanine is like, you didn't put two alanines side by side, and alanine dipeptide means a peptide with two alanines. I mean, yeah, polymerized. So really,
Good.
to me,
then we have that
anyway.
Part of the discussion also settled. I think this is a question that only maybe two people here in this call care about. And yeah, let's say thank you for all the nice questions. Thank you for the nice presentation and the nice discussion. And if you have some last words, then now's the time. That's a no.
I think everything's been said.
Perfect. Then thank you very much for the nice talk, and
thanks a lot for inviting us.
Guillaume, Jerome. I hope we'll chat again at some point and see more interesting work in the future.
Pleasure.
Thank you.
Thanks. Bye.
Okay, great discussion about Boltzmann generators, and maybe we will come to see the day where Boltzmann generators are actually useful. Yeah, and if you want to join future reading group sessions yourself, all the information is down in the description. And with that, have a nice day, friends of the sun, and see you.